But what I have up on the smartboard is two different ways to show the same thing. So notice one in word form says cobalt 57. The other one is 57 as a superscript, so up high, and then CO, the symbol for cobalt. And you can see on this slide, I'm just showing cobalt, and then that 57 is the mass of something. What we have to go over today is if I give you a symbol like either of these, you should be able to figure out the number of protons, neutrons, and electrons that that thing contains. Okay? So this is just kind of the introduction of here are two different ways to show the same thing. When we get to the next slide is when I think we need to jot down a couple of things, and I'll try to tell you which things I deem more important, just so we don't have to spend a lot of time looking at each slide. If I happen to go a little fast, again, feel free to just watch this afterwards, or quite frankly, I can just show you the slides again later on. Okay. Cobalt 57 on the very top. Let's talk about that a little bit more. What I say in a sentence form right below it says cobalt 57 rather, is the mass of an atom is due to the protons and the neutrons. This goes back to a reading guide that we did at the beginning of this unit where electrons basically have no mass. What I think would be worthwhile to write down in your notebook is this kind of equation I have here. The mass of an atom equals the protons plus the neutrons. And to me, that's the first thing that you really might want to note. And this is the shorthand notation for protons because protons have a positive charge. So P for proton, plus sign for positive. Neutrons, N for neutron, neutrons don't have a charge, they're neutral. That's why it's a 0 up there. But when I say cobalt 57, that means a combination of protons and neutrons added together will give me a mass of 57. It's just a matter of counting how many protons I have, counting how many neutrons I have. Right below my kind of equation that I wanted you to write down, the protons are already on your periodic table. That's the atomic number. So, for example, Gnorski has a periodic table out in front of him, right? Is it opened up so you can actually see it, or where you put it away? He's going to find cobalt right now. Found it? Yeah. The atomic number is the number in the corner that's blue. It's the biggest number there. What's that number for cobalt? 27. That means cobalt has 27 protons. The atomic number is the number of protons. What you're going to learn today is that the neutrons can vary for an element. That's called isotopes. The electrons can vary for an element, so you can have ions. However, the protons stay the same. 27 protons is the identity of cobalt. Like its DNA, if you will. It's what's on the inside that makes it what it is. The outside can still change, just like you can get a haircut. You can change your hair color from the beginning of the year when I first met you. So we can do different things about ourselves. We can change our clothes, but the inside stays the same. Hydrogen has 1 proton. Helium has 2. All this other stuff doesn't matter. To determine the element, you look at the atomic number. If we know the mass and we know the protons, we can solve for the neutrons, which is what my last thing says here. Neutrons are calculated by taking the mass, remember this one is 57, minus the protons. So in this particular problem, for cobalt 57, how many neutrons does it have? 30. This isn't meant to be groundbreaking here. This is meant to be hopefully having you identify how to figure this out, and we'll practice this a little bit. But if you can find an element on your periodic table, you know the number of protons. 57 is given to us for the mass, so we can solve for the neutrons. Are we okay with that? Because that's the easier of the two things to find. All right, so we can find electrons as well. And electrons, as I state in this first sentence down here, the charge of the particle is due to the protons and the electrons. I'm showing you two examples here. Notice where the purple circle is on both examples. If something has a charge, we would write it where that purple circle is. So in this bottom example, this cobalt has a +2 charge. This upper example, there is no charge, so we just leave it blank. If an atom doesn't have a charge, its protons are the exact same as its electrons. On this cobalt 57 here, we said, when you look at the periodic table, that it had 27 positive protons, the atomic number. Since there is no charge, there is nothing inside of this space right here. The electrons, which is a symbol of a lowercase e with a minus symbol, would also be 27. Because the positives and the negatives would balance out to give no charge. Does that sound okay? The part that throws off students, which, again, if you were to write something down, your second quote-unquote equation would be this equation down here. To solve for the charge of something, you take the number of protons minus the number of electrons. So I'm giving you an example on the bottom of this slide here, and I can scroll this up a little bit if that helps out, of cobalt +2. If it's a +2 charge, that does not mean that it gained protons, because protons don't change. The number of protons for cobalt is always the same. It's always 27. If my charge is a +2, how many electrons does cobalt +2 have? 25. This isn't tricky math. However, this is the thing that throws students off the most. When they see a +2, they want to say 29 electrons because they gained 2, right? No. Electrons are negative particles. And if you gain a negative particle, you become more negative. On the other hand, if you lose a positive particle, if you lose a negative particle, you become positive. Which is why, Justin, I even wore subject-specific clothing today. This guy says, I lost an electron. And this guy says, are you positive? Justin made a little bit of noise, Maya. You had zero response to that. If I can't wear subject-specific clothing with really lame puns on it and not get a response at all from you, Maya, what am I doing here? Come on, it could be a groan-up. Oh, that was bad. I just need something from you here. Not just Maya, all of you guys. Come on. Bova, come on now. Respond to this. It's the most common mistake students make, though. When you lose a negative, you become positive.
What is it, like, what's the +2?
The +2 represents the fact that this version of cobalt lost 2 electrons, so now it has a charge. It's what we call an ion.
So why is it say +2 then?
Because overall, there are 27 positive protons and 25 negative electrons. So there's a net charge of +2 because there's more positives than negatives. Because when you have a positive charge, that's what it means. You have more positives than negatives. But remember, the protons don't change. It's only the electrons that change. So the top version, this is a neutral atom. An atom has equal numbers of protons and electrons, so it has no charge. An ion has a charge. And that's actually maybe the last thing I want you to write down for quote-unquote notes today is the definition of an ion. An ion is a particle, again, that could be an atom, although it could be bigger than that, that either gained or lost electrons. If you gain or lose electrons, you now have a charge. Again, I don't think you have to write down what's in this box on this slide here, because that's a little bit more wordy. We'll talk a lot more about ions in future class periods as well, because starting next class period, our focus will be more on electrons than anything else. However, in order to determine the number of subatomic particles for things, we have to go over this today. So remember, if you lose a negative electron, that will make the atom a positive charge, because you have more positive protons than negative electrons. If you gain a negative electron, then you become negative. And as I have in all caps in the bottom, the protons don't change. What I just went over with you is meant to be kind of a skill. A skill where if I give you a problem where I ask you how to identify the number of protons, neutrons, and electrons, you're able to do that. And what I'd like to do is 2 practice problems with you right now to demonstrate that. And again, if people wanted to write more than this, I'll come back to this slide a little bit later. But what you see up on the board is one way that we can assess this. We can assess your ability to determine the number of protons, neutrons, and electrons that something has. In my mind, starting with protons is the easiest because you look at the element. Now, Gnorski already covered 1. I need somebody else. In this lead-210 with a +4, how many protons does it have? This requires your periodic table out unless you have this memorized already. Justin? You have to look. PB. 82. Okay. We know 82 protons because the periodic table says so. The atomic number is the number of protons. Neutrons. You take the mass, 210, minus 128. And the last one is what we have to be a little more careful about, the electrons. If this ion has a +4 charge, 78. Remember, protons are positive, electrons are negative, so this has more positives than negatives. Let's do one more together. 31 sulfur -2. Someone we haven't heard from. How many protons? Look at your periodic table. 16. Somebody else, we got to do a little subtraction. Let's solve for the number of neutrons. Ben? 15. And one more person. Electrons. Notice that's a -2 charge.
17.
Protons plus the 2, not the neutrons. Okay, so what I would like to do with this isotopes packet is go over the front page with you, and then the rest of it I would like you to work on your own with each other, again, however you choose to approach this. To start off with, it gives you the definition of an isotope at the very top. Isotopes are atoms of the same element with a different mass. This occurs when they have the same number of protons but a different number of neutrons. That results in a different mass. That's just what you practice. Again, an element with the same number of protons is the identity of a thing. If it's 6 protons, it's carbon. It doesn't matter how many neutrons it has. It's carbon if it's 6 protons. However, the mass can vary. The mass varies due to a different number of neutrons. Now, in this middle section here, they show you 3 different ways this can be shown. Again, I showed you this first and this third way a little while ago, but this is another way you could show an element and its mass. Okay? Let's look at this middle table. It says, using the notation above as reference, fill in the chart below. So in other words, I want you to take a minute right now. Iron 54, figure out the number of protons, the neutrons, and the mass number. Iron 56, same thing. Same with iron 57, same with iron 58. This large column on the far right-hand side we'll kind of address in a minute. So again, take a minute to fill in protons, neutrons, and mass for these 4 isotopes, which means it's the same element, but it has a different mass because it has a different number of neutrons. So again, we could fill in that 54 if we wanted to, 56, 57, and 58. Now, what it says up here, the atomic weight for any element can be located on the periodic table. Remember that mass that we used for molar conversions? That's the atomic weight, or the atomic mass. What is that average atomic mass for iron? Let's go to the hundredths place. So what number do we use for mole conversions for iron?
55.85.
55.85. Now let's look at that second to last column. Percent abundance. What we know looking at this table is that there's 4 naturally occurring isotopes of iron, 4 different versions of iron. Some are more abundant than others, however. Because some are more abundant, they play a larger role in the average mass. An average mass on the periodic table does not take the 4 isotopes, add up their mass, and divide it by 4. If it did, this average mass would end up being not 55.85. The average mass in the periodic table is what we call a weighted average. If something is in a higher percent, that should play a larger role in the average. I like to use the example, if we did the age of people in this room as a sample altogether, there might be some 15-year-olds in this room. I know there's 16-year-olds in this room, and there might be 17-year-olds in this room, and I know that there's at least one 40-year-old in this room right now. If we took the that's me. If we took the average of these different ages, our average as a class would be in the high teens. However, if you took any individual in this room, odds are you're more likely to get someone who's 16 than anything else. 16 is probably the closest average in this room. I throw off the results because I'm older. But I'm a low percentage of individuals in this room. Periodic table takes that into account. Whatever is the highest abundance, in this case iron 56, that isotope is closest to the average, 55.85. So when this question right below asks about that idea of percent abundance, that's what I'd like you to address. So again, the question on the right below the table says the abundance of an isotope indicates how common it is on Earth. According to the table above, what is the most common isotope of iron? Well, that's iron 56. Okay? Last thing we're kind of doing together before we break out. I don't even need to read this top direction point. I'm just going to talk you through it. The atomic weight in this first blank column is that average atomic mass from the periodic table, that mass that you use for mole conversions. So what you're going to do is you're going to look at your periodic table and you're going to fill that in for helium through carbon, which is elements 2 through element 6. Then, what you're going to do in this final column is you're going to think about which isotope is the most common for that element. And what this suggests doing is rounding the average atomic mass to the nearest whole number. So for example, the average mass of hydrogen is 1.01. Well, that's really close to 1. So the most common isotope of hydrogen is hydrogen 1. I'd like you to take a couple of minutes to look at your periodic table, fill in the averages, and then think to yourself what whole number is closest to that to represent the most abundant isotope for those elements. So to fill in that first blank column, all I did was look at my periodic table. Then from there, the most common isotope is whatever the closest whole number is, which for helium would be helium-4. Bova, what would it be for lithium?
I said I'll have 7.
Yeah. Round that up to 7. Justin, what would it be for beryllium? 9. Mariah, what would it be for boron?
11.
And carbon would be 12. Okay? What you are going to do, starting on page 2, it's going to show you the equipment used to figure out these different isotopes and their percent abundance. Because after all, atoms are too tiny for us to really get a good measurement on, so there must be something used to detect this. Page 2, I'll come around and help out with a little bit. If we struggle a little bit, though, that's not a big deal. Pages 3 and on are showing you graphs, showing you data tables, different ways to relate percent abundance to the average atomic mass on the periodic table. So if you're going to break out and work on this, bring your periodic table along to help out. I'm going to get us back together with about 10 minutes to go because we have a second activity to do with isotopes to wrap this up. All right, so go ahead.